Okay, so we're going to talk now about rotation. So let's go into some of the important stuff there. So this again is an important equation for us for rotation, relating the time for one full rotation to the number of rotations per second and the number of radians per second. Let's see other rotation stuff. So this is how you calculate the rotational kinetic energy of something. We can do rotational kinematics if you have a constant angular acceleration. Same thing with this equation right there. Here we have centripetal force or centripetal acceleration. So remember, if you're rotating, tangential acceleration would be the acceleration this way, okay? Whereas centripetal acceleration is the acceleration this way, the amount of acceleration you experience due to the fact that you're rotating. This one right here is how the speed of rotation is changing. Let's see, other rotation stuff. Okay, and so when we talk about rotation, we can measure how difficult it is to rotate something, and that measurement is called moment of inertia. We use the capital I for that. And for rotation, for any system, angular momentum has to be conserved. And this is kind of a very powerful principle that's going to come up in some of the questions. And then finally, this equation right here is how we relate angular and linear quantities. Now there's only this version of it, but we also know that we can do this, that S, or distance, equals to r theta, as well as that A is equal to r times alpha. Okay, and so we can use, these are all kind of different variants of each other. Okay, so anyway, for rotation, we will do a free response together on this one, but before that, I'll just do some review with moment of inertia. And so we'll actually do, I know it's an oscillation question, we'll do a question with the physical pendulum. So let's say that we have a meter stick, okay, with a mass of, we'll just say little m. And then at the end, there's a larger mass attached. And we'll say that this one has a mass of 3m. And we're going to say that this length is 1 meter. Okay, so we want to find the moment of inertia of this system. The center of mass of this meter stick would be right here. Okay, so because this meter stick is, we're going to say it's a pendulum, so it'll be oscillating about the top right here. Since its axis of rotation is not about its center of mass, then when we find moment of inertia, we have to use the parallel axis theorem, which we get by adding the moment of inertia about its center of mass plus mh squared. Okay? And so for this one, it's a meter stick. The moment of inertia for a meter stick is 1/12 ml squared. Okay? We're going to add to it mh squared because it's off its center. And that would be the moment of inertia for this. And then this right here we would treat as a point, since we don't have dimensions for it and it's relatively small, and it has a mass 3m. And so when we find moment of inertia of a point, we just use r squared. So that's 3m, and then r is going to be equal to 1 meter. We'll just call it L. So we'll say L squared. Okay? So now we have to plug in some other values. This h here is going to be equal to the distance that the meter stick is away from its center of mass. It'll be this distance right here. So it'll be that distance L over 2. So we get 1/12 ml squared plus m times L over 2 squared plus 3 ml squared. And this 3 ml squared came from that piece right there. So we'll simplify this part. That becomes 1/4 ml squared, 1/12 ml squared, and then 3 ml squared, okay? So a 12 plus 1/4, 1/4 is 3/12, this is 4/12 combined to get 1/3 ml squared plus 3 ml squared. This one is for the meter stick, this is for the mass at the end. We combine them, we get 3 and 1/3 ml squared as our moment of inertia. Alright, so we're going to start off with this first question from the packet together. So we have this rod here. Okay, it's got a block attached to it. It's attached to this disc, which is hooked by a string to the wall. Okay, and so we have kind of this weird system. I'm going to try to draw the forces acting on it. So we have on this, which is fixed to the wheel, we have a torque that's acting kind of about the center of it, I suppose. Let's see, the disc has radius r, and the rod has mass radius 2r. So that means that this distance right here is half the distance of the rod. So this string is kind of pulling at this disc, which is supporting this rod, which has this block attached to it. So we have this kind of weird system in equilibrium. And what I want to focus on, though, is that it's at equilibrium, which means the net torque is 0. So I kind of want to show the forces acting on this rod and this block. So we have the weight of this block, we have the weight of this rod, and then we have this force of tension here acting at about the radius, and then we have some angle right here, theta. Okay, and it asks us to find the tension in the string. Well, if this system is in equilibrium, okay, then what that means is the net force is 0, and so the net torque is 0 in this system. So the sum of these torques would have to be equal to 0. Okay, so 0 equals T times R. Now this is going to be acting at an angle, and so we would say that if this is distance R, that it is away. Sorry, when it comes over and it's acting at the axis of rotation here, it's a distance R away. So I think we can actually say that it's just T times R. I think we can ignore the angle, because it's acting perpendicular here to the disk, okay? So we get TR from that minus mg, or 2m for the block, okay, because it's head mass 2m. So 2mg, and then this angle here is going to be theta, the same as that one, and so we use times sine of theta to make it perpendicular, and then we'll, for the rod it has mass m, we'll do the same thing, minus m times g times sine theta, and we gotta multiply by the radius, so the block is at a distance of 2r, and this one's at a distance r, and so that gives us our net torque equation. We can solve for t. R is going to divide out of the equation, and so that t is equal to 3 mg sine theta. Okay, so now it says the string is now cut, so we're going to cut this string, and this thing is going to start rotating. And we want to find the magnitude of the angular acceleration of the disk, which will be the same of this system since it's fixed. They'd all have the same angular acceleration, and the magnitude of the linear acceleration of the mass at the end of the rod. Okay, actually, and just real quick, I noticed I made a mistake earlier. Let's see, that was 2r, so 2 times 2 is 4, and 4 and 1 is going to give us actually 5 mg sine theta for tension. Okay, so anyway, for this system here, now it's in accelerated motion, so I alpha equals, and then the two torques now are just from these two forces, the weight. So we have basically this amount right here, the 5 mg sine theta. Okay? And now, to solve for this, we would need to because we want to find alpha to answer part 1 here. So I would be the combined moment of inertia of this system, because the weight of the rod and the block is causing everything to rotate. And so I is going to be I of the disk, so 3/2 mr squared for the disk, plus for the rod, 4/3 mr squared, and then plus for this block, we treat that as a point, so just mr squared, and then the r for that one is going to be 2r, because it's a distance 2r away, and the mass for that one is 2m. So it would be 2m times 2r squared, and all that times alpha equals mg, 5mg sine theta. Now before we simplify this, I just want to remind you, if we had to find moment of inertia here, for a disk, moment of inertia would be 1/2 mr squared. For the rod, it would be 1/12 ml squared. And since it's rotating about this point, we'd have to use parallel axis theorem, so plus mh squared. Okay, so let's simplify this. 2 times 2 squared is going to be 8 mr squared. And so 3/2 plus 4/3 plus 8. So 3/2 plus 4/3 going to give us, let's see, that'll be 1 3/6 plus 1 4/6, which is going to be 2 7/6, or 3 1/6, plus 8 will give us 11 1/6 mr squared equals 5 mg sine theta. We got our alpha right there. Okay, and so now to solve for alpha, m is going to divide out. We'll just do some quick calculations here. So if I divide all this stuff over, I get that alpha equals 0.45 g sine theta over r squared. Okay, that is alpha. Okay, and from here, oh, you know what? I made a mistake. Okay, so the problem I made was that this is equal to t, okay, not equal to the torque. So this would be times that radius r, because we divide the radius r out. Okay, which means that we have an r right here. So one of those r's will cancel. So 0.45 g sine theta over r is what alpha should be equal to. Okay, and then from here to find linear acceleration, we say that a equals alpha times r, and so we multiply that by r and get a equals 0.45 g sine theta. Okay, for the last part, it says determine the speed of the mass at the end of the rod for the instant the rod is in the horizontal position. Okay, so we know that it's going to travel an angle of whatever this angle is, so this would be 90 minus theta. I'm almost out of time on the video, so I'm just going to discuss options here. You could do two things. You could look at conservation of energy, so mgh equals 1/2 I omega squared, where h is whatever the location of the center of mass is for this system. We would use that and find that change in height to get to that horizontal position, and you'd use that for h here and solve for omega. The other option is, since we know what a is, we can solve for the distance it's going to fall. Okay, so this is length r, so this would be r cosine theta right here. So if that's r cosine theta, we can use that distance and that acceleration and use kinematics to solve for the velocity.